and welcome to this film about spectral analysis. So today I'm going to be discussing an analytic tool called spectral analysis. And we're going to talk about two different types. We're going to talk about one, mass spectroscopy, and the other one is going to be then molecular spectroscopy. And molecular spectroscopy actually has, we're only going to discuss two types. We're going to talk about two types of molecular spectroscopy, and one of them is going to be then infrared or vibrational absorption spectroscopy, and so that's A, and B, resonance or HNMR spectroscopy. Now, each one of these types, it doesn't matter really what we're trying to do then is we're trying to look at the first type, mass spectroscopy, is then determining the mass of sample compounds and their components. Okay? So oftentimes when we talk about compounds, we're talking about one thing, but when we talk about molecules, then we also talk about their components. And then two, we're going to use them to determine molecular structure. So the first one is used to determine mass, and the second one is to determine molecular structure. Both of them don't, but we can also say that basically this entire topic is about the interaction of electromagnetic radiation with matter. This is to a lesser degree with mass spectroscopy, but to some degree it's true there too. And if we're going to talk about then the interaction of electromagnetic radiation with matter, we have two types, right? Light, which is what this is, right? It's light, can either be absorbed or it can be emitted. Now, by matter. So if we take and we add energy to a sample and it gives off light, then that's called emission. So then we can have emission spectra. But we can also have some other things like if you add energy, you can also get changes in heat, for example. Then you have absorbed. You can have the absorption spectrum, which is proportional to the transmission of light. So light can be absorbed, can go into something, and then it can be absorbed, but the light that makes it all the way through is then considered to be transmitted. So different materials react different ways when they're exposed to light, and we'll talk a little bit about more of that when we get to molecular spectroscopy. Okay. So let's talk a little bit about the first type that I want to talk about, which is mass spectroscopy. So mass spectroscopy basically builds on the idea that you can accelerate a charged particle, and when you accelerate a charged particle, you can get it to change its direction using a magnetic field. So basically, you have an apparatus, and I'm going to draw the apparatus for you first here. So we have an apparatus that can be broken down into different stages, and then we can talk about how they're broken down and what they do. And so what you have is a long tube that has a bend in it. And these can be made out of different materials, glass or some other thing. And basically what is happening then is that you enter a sample into your machine here. Let's say I have a sample of that's composed of two different parts, or it can be two different atoms, or it can be a sample with two different molecules in it. You can do all sorts of weird things with these things, but basically then, so here we have a sample that's composed of these two things. The first thing that is going to happen then in this machine is that the sample, whatever it's made out of, is going to be vaporized. So vaporization is going to occur. Now, vaporization is going to occur a little bit easier in this case because this tube is already under reduced pressure. So it's kind of a vacuum. It's not a complete vacuum, but it aids in vaporization because, of course, if you heat this up, it's going to turn into a vapor, especially if if there's a reduced pressure inside of here. Once it's turned into a gas, the particles are kind of separated from each other a little bit, or the different atoms are separated from each other in some cases. In some cases they're sitting together. We'll get into the more details like that in a minute. And what happens then is that it enters into a section of the machine, the mass spectrometer, that basically ionizes it. So there's ionization takes place. And the ionization usually takes place by electron bombardment. So basically you shoot electrons at your sample, and the electrons knock off the electrons in the sample, so these become charged particles. And we'll just talk about that in just a minute. Sometimes it can be or X-ray. That's another method. Any kind of ionizing radiation then. So what basically happens then to these little particles in here is that they all become positive. The electrons are stripped off, or some of the electrons are stripped off, so all these little now vaporized particles become charged. And what you then can able to do if you have a charged particle is that you can accelerate them. And you accelerate them by electrical field. So they're accelerated by an electrical field. So they start to shoot down this tube. They start to accelerate, and then they reach some sort of velocity. And so now you have a charged particle that's traveling down this tube. Now I'm only going to illustrate two of them, obviously, at a time. But when this is normally occurring, all of them are moving, right? So you have hundreds of these, if not thousands, and in some cases millions of them, depending on the size of your sample. Now, as they go barreling down this tube, literally, what they encounter then is a magnetic field. And I'm going to draw the magnetic field as if it were like a big horseshoe magnet here. And we can draw it like this, right? And so we have this magnet. And the magnet then, and to illustrate this clearly then, I'm not going to go into the north-south thing, but basically what we have then is we have a plus side and we have a minus side. And the positively charged particles are going to be attracted to the negative side of this magnet and repelled from the positive, and so these are going to be deflected. And they're going to be deflected along this tube, and they're going to be then deflected differently due to their mass. So there's going to be a difference in the degree of deflection that is based on, that is proportional to the mass of the ion. So the degree of deflection is proportional to the mass of the ion. And so if the red, in this case, in our example, then the red one is slightly heavier, it's not going to be deflected as much. And the blue one is going to be deflected more because it's lighter, which I've sort of failed to illustrate here. But the idea is then that they come from the same source and they're deflected differently depending on how heavy they are. So then we have then, this is deflection. And then at the end of here we have what we call ion traps, and these are like little devices. In fact, they're microchips usually nowadays that act as then detectors. And those detectors then can be tied to a computer or another computer, and then that computer will read these and it'll tell you exactly where these are. And since these are calibrated, then these can, you can know exactly how heavy each ion is. And this is basically how the mass spectroscopy works. And this is what a mass spec machine looks like, sort of in a diagram. Now, what can you use these to do then? Well, let's look a little bit at the different types of ways that you can use a mass spec to determine different things. So we'll look first at a very simple molecule, and then we'll give a more advanced example with actually even simpler. So let's look at this hydrocarbon. And look at what we can learn from a mass spec readout from this, or we can elucidate it. So in this case we have then 2-methylpropane. The methyl group is on the second carbon, and we have an atomic mass, a total atomic mass of 58 AMU. if we look at it, then we can see that this part here is 15. And if we look at this part up here, it's also 15. And this part here is 15. So we have 3 parts that are 15. And then we have this carbon with this hydrogen together. Its mass is 13. If we just do that part here. So if we were to look at this, and we're sort of backwards engineering this mass spec diagram, we could see then that the mass spec, if everything was working the way it's supposed to, and we're going to ignore isotopes in this case, then you'll get a peak at 58. The size of this peak will depend upon how hard the ionization process was, or how strong the ionization process was when you did the actual test, the test of the sample. Because if you have a higher ionization energy, meaning that if you use more ionizing radiation, or increased in number of electrons that are bombarding this molecule, then what happens is that these bonds will break. Now, if you don't use very much of that stuff, then you just knock 1 or 2 electrons off of the whole molecule, and you'll get the mass of the whole molecule, which is around 58. There might be a few little peaks around it that represent then different isotopes of carbon. For example, you might get, at 1% you get carbon 13, so you might get a little bit of carbon 13 or something for each of the peaks that we're going to draw. But I'm going to ignore those for now. So on the other hand, though, if the ionization of this molecule was pretty effective or strong, then you might get a bond that breaks here. So you would break that bond. Now if you break that bond, then obviously you're going to get 2 pieces. You're going to get this piece and you're going to get that piece. And so this piece, the one that is broken off of the larger piece, has a mass of 15. So you could expect in a mass spec that you would get a peak at 15 from this molecule. In fact, it'll become clear that you will absolutely get a peak at 15 in just a moment. But if you get a peak at 15 and the rest of this molecule remains intact, then it becomes 58 minus 15, which is then 43. So if you get a peak at 15, there's a really, really, really high likelihood that you will also get a peak at 43. Because the rest of this molecule weighs 43. But if this bond breaks, then there's a high likelihood that this bond will break as well. Or this bond will break, and that one won't break. It depends, right? So you get a bunch of different problems here, because what you end up with, if this bond breaks, then you get a piece that's 15 also, and the other piece again is going to be 43. If this bond breaks, but these don't, you get the same situation. So the likelihood of getting a 15 is really, really high. In fact, the peak at 15 might be really strong, because, or it might be a very high peak, because if this bond breaks, then probably all 3 of them will break, or can break, and so you get a really high peak there. But if you get that peak and all 3 of them break, let's say every single one, this one, that one, and that one all break, then you get 3 pieces that are 15, and you get 1 piece here that is 13. So you'll get a peak at 13 as well. So you're going to get a peak at 15. You're probably going to get a peak at at 15. You're going to probably get a peak at 13 if these break. But there's also a likelihood that what could happen is that 2 of these break and 1 of them is retained. So then you also get a peak where it's 15 plus 13. So you might get a peak at 28 as well. And that can be for either, so if two of these break and the rest of it stays intact, you get a 28 each time. So a mass spec diagram for this particular molecule, depending on how strong the ionization is, will look something like this. You'll get a peak at 58 for the mass of the whole molecule, and then varying degrees of breakage depending on where which bond has broken. And then you could probably put this molecule together. If you had practice and became skilled at looking at this kind of diagram, you could probably put this together. Now, let's look at another example. So this is an example where you look at the molecular structure. A mass spec can also be used to determine the isotopic ratios. We're going to look at chlorine, and I'm not going to do the isotopic ratios. I'm going to also backwards engineer this problem. So I know, and I'm going to tell you now, that chlorine has two isotopes. And those isotopes are Cl37 and Cl35. And the average atomic mass for chlorine is 35.5 AMU. So if we want to determine the relative proportions of these two, we can actually go to a mass spectroscopy and see the relative proportions if we wanted to directly. But in this case, I'm going to actually work it through the problem from in a little bit different way so that we can illustrate the whole problem. So if we have these two proportions and this is the average, then we can determine then that the total number, the proportion of each one of them has to equal 1, right? 100%. So there has to be X amount of this and Y amount of that, or vice versa, and they have to add up to 100%. So then you can take 37X plus 35Y and get 35.5. And if we solve for this then, and we say that, let's say that we want X, we set X equal to something, we can say that X is equal to 1 minus Y. And then we place that in by replacement here. So we get 37 times 1 minus Y plus 35Y equals 35.5. And if we solve this equation through, then we get 37 minus 37Y plus 35Y, 35Y equals 35.5. And if we solve this through, then we get minus 2Y equals minus 1.5, which means that Y is equal to 0.75. Put that back in. We realize that the proportion of Cl35 then, Cl35 is 75% of all chlorine, and Cl37 is 25% of chlorine. This is not exactly accurate, but because the actual mass is like 35.45 or something like that, but we'll ignore that for now. So then let's look at what a mass spec readout would look like given this data that we have now gotten. Actually, I've given you. So here's our mass spec. And so if we looked at it and we looked at, okay, chlorine is put in there. It's put in as chlorine gas. So chlorine gas can come in 4 different forms, or actually it comes in 3, but you have to think about the fact that it might be, there's there's a little issue here that we need to discuss in just a second. So you have the probability of getting chlorine with chlorine, and that's going to be then 0.75 times 0.75. And then we have the likelihood of getting chlorine 35 with chlorine 37, and that's going to be then 0.75 times 0.25. But you also have a likelihood of getting chlorine 37 with chlorine 35, which you would think that they're the same, but they're actually not, because you have the likelihood of this one being with that one, or this one being with that one, and they're not. They're different opportunities, so to speak. And then we have the likelihood of chlorine 37 being with chlorine 37, and that's going to be then 0.25 times 0.25. If we look at the mass spec diagram then, first you would have a peak at 35, obviously, because the chlorine has been broken apart, ionized. So then that peak would be about 7.5, and the peak at 37, relatively speaking, would be 2.5. 0. Would be 2.5. Now, it wouldn't necessarily be like that. It could be 0.75 as well, but that's a different issue. But then if we take these, we'd realize that together 35 plus 35 is 70, so there's going to be a peak at 70, a combination of chlorine 35 with chlorine 35. It's going to be the result of 0.75 times 0.75, which is 0.5625, I think, something like that. And then you'd have a peak at 35 plus 37, which is going to be 72. That peak is going to be then the combination of these two. You have to add them together, and that's going to be 0.375. And then you're going to have a really, really small peak at 74, and it's going to be then 0.0625. Now these are just proportions to each other, right? So they could be 5 to 3 to 0.6 or 0.6, or they could be 56 to 37 to 6. It depends on the scaling of the machine or the readout of the machine. So this is an example of two examples of what you can do with a mass spectrometer, and to make them work. So I'm going to leave that topic and then move on, but this is something that you can work on in other examples later on. So then I'm going to leave then the mass part, and now we're going to move on to then looking at molecular structure. Now we looked at the masses and we saw that we could break it up and see the different parts in masses. Now let's look at what you can do with the structure. So the first type is going to be the easiest type, which is then what we call infrared absorption spectroscopy. This is also sometimes called vibrational. Now, it turns out that infrared radiation, or frequencies of light in the infrared band, when they interact with molecules, particularly with covalent bonds between the covalent bonds basically, they interact then with the energy of the covalent bond. And they get absorbed by the covalent bond. So there's an absorption here that takes place. And so what that does basically, in the simplest terms, is that any covalent bond, if it be between two carbons or between two oxygens or whatever it is, will cause then a vibration here. This vibration then can sometimes be measured. It cannot be measured if the two atoms are the same. So this does not work for what we call homonuclear bonds. For example, it does not work with hydrogen gas. It does not work with O2 gas. It doesn't even work with something like ethane very well. It depends on if there's any isotopes actually, but so it doesn't work with that either. Because in order for this system to work, then there has to be a difference in the mass of the two atoms. There has to be a difference between the two atoms that the infrared radiation is interacting with. So this infrared, so the infrared radiation corresponds to the energy needed to cause the bond to vibrate or oscillate even, if we will. So if we want to think about that, then we can think about then the two atoms that are involved, and we'll just do a really simple one here where we say, okay, if we regard the single bond or the double bond for that matter, it doesn't matter really what kind of bond it is, we consider the atoms that are attached, and we're not going to go into what atoms they are, it doesn't really matter in this case, right? We can imagine them being attached by a spring. So the spring then, if you add energy to the spring, then there's two or three things that can happen, but I'm going to talk about the first two first here, right? You can get a compression, right, where the spring gets smaller. This is one option. The second option is that the spring extends, right, and gets longer. And there's a third option that I'll discuss in a minute where the bond starts to sort of swing. So you get but in order for that to be true, then we have to have some other relative position. So we have to have a second atom attached to the central one. So this one, if this one's going to swing back and forth, then there has to be something else that it has to be relative to. We'll talk about that in a moment. But anyway, let's talk about these first two options, right? So this is compressed, and this is stretched. And when it's compressed, what you get is the masses are very close to each other, and so what we get a small dipole moment. So we have a small dipole moment. And this can be measured, basically. And I'm not going to go into what that means, but I mean basically, and when they're stretched, when these two masses are very far from each other, then we have a large dipole moment. And when this is occurring, when you've added the infrared radiation, um, basically what can happen is that the machine can then measure where this absorption is taking place. So, and it can only measure that if there's a difference between the two atoms, so that there is actually a dipole moment between the two. And this oscillation between these two states is sufficient then to determine, is unique, I should say, is unique to each type of combination. So if this is, for example, if this were a carbon attached to an oxygen, it would be a different amount of energy in the dipole change here than if this were a carbon attached to a nitrogen. And so you can measure that. And that leads to some interesting things that you can measure then. So when you look at then IR absorption spectra, and I'm not going to go into too much detail with this, but it basically, you can look at a graph then, and the graph is unique to each type of molecule. So a lot of times these molecules will have some sort of like really a lot of noise here, and it's not actually noise, it's just that you can't really measure these peaks. So these peaks are what we call a fingerprint. And even though we can't really determine what these are showing exactly because they're all overlapping with each other, the fingerprint is actually unique. So the fingerprint region is unique to pure samples. And there are actually databases. So all you really need is if it's a well-known molecule, you can just look at the fingerprint region. The database will know what the fingerprint region is saying, and it'll tell you what the molecule is right away if it's a well-known molecule. So for example, if it's some sort of drug or a well-known medicine or something like that. I mean, this could be an illegal drug or it could be another medicine or something. It'll know. The machine will be tied to a database and it'll tell you right away, okay, this is, aspirin or heroin for that matter. But if you're an analytical chemist and there's no fingerprint region there that you can read, or it's not in the database, then the region that's outside of the fingerprint region is going to be where the peaks that you're interested in are. And then these peaks then will be identifiable. Right? So these are going to be identifiable bonds. And a lot of times these identifiable bonds are things that you need. Of course, you need a table. You need values to compare it with, right? So you need to compare values. And they're typical. So the amount of absorption is very typical for each type of bond. So it really works well with things like OH groups and NH groups and N groups like this, amines and amides, phenols, all sorts of different molecules. So it's very, very useful. This type of spectroscopy is very useful for what we call identifying functional groups. So I'll just write that. Very useful in identifying functional groups. And this can be very helpful when you have the combination, for example, with your mass spectroscopy. You can find out, okay, so we have this mass that is like, for example, here, your mass spec says that there's something that weighs 17, and your infrared absorption spectrum says that there's an OH group, then in all likelihood then that mass that you have that is 17 is an OH. And you can use it that way in combination. So the third and last type of spectroscopy that I want to talk about is then something called resonance spectroscopy. Now, resonance spectroscopy relies on the idea that, first of all, let's get some things straight here. So you have to have, in a resonance spectroscopy, you have to be looking at samples that have atoms that have uneven number of nucleons. So that means that the number of neutrons plus protons has to be what? Odd. Has to be an odd number. So typically then in organic chemistry, and there are other examples where you can use this with other atoms, but typically what you look at is you look at H, which is super common, it's everywhere, and then you look at carbon 13. Carbon 13 is an isotope, right? It's an isotope with an abundancy of about 1.1%. So it's not very common, so you have to have pretty large samples in order for this to work effectively, and it doesn't work as well as you would like. But on the other hand, these machines have become so much stronger in the last 30 years, the last 15 years, that they work really well nowadays. So obviously in hydrogen you have one proton, so that's an odd number automatically, and in this isotope you have 6 protons plus 7 neutrons, so you have an odd number. I'm going to do the example now with hydrogen, and then we can talk a little bit about carbon in just a moment, right? So H plus, the nucleus in H can adopt 2 orientations. And what we mean by this is by spin. And so it can have a spin of either up or down. There's lots of ways to do it. There's another more official quantum mechanical way of saying it, where it's like sort of m equals 1/2 or m equals minus 1/2. So you have 2 possible positions. But regardless, this makes it active, NMR active. And since, if we look at this then and we see, okay, it's NMR active for sure, but if you look at the total number of samples, you get up on the order of, at normal energies, a normal sample is going to have just almost an equal number of atoms with both orientations. And what I mean by that is basically that you're going to have just as many that have the one orientation versus the other, right? So they're almost the same. So if they are almost the same, then the transition, right? The transitions from one state to the other are going to be non-measurable, basically, under normal conditions. You're just not going to do it, right? But if you put these things in a magnetic field, right? Then the change in energy from one state to the other increases, right? And it increases in proportion, basically, to the applied magnetic field, right? So, which makes then the transitions from one state to the other easier to detect because the energy change is higher. So let's kind of put this in perspective then. We got a little bit of the theory there. Now let's put a little more theory here. So let's draw then a situation that we're kind of analogous to what we're talking about. So here we have a magnet. So like a horseshoe magnet. And here's north, and here's south. And then we have a bar magnet in the middle here. And this one is in the unfavorable position. So north is pointing at north, and south is pointing at south. Now this is high energy. Right? Now, obviously, if you increase this magnetic field, right? If this is, then flipping this over is going to release more energy. And so if we compare that then with the low energy situation, and you put a magnet in here, and this magnet has the favorable or the low energy version, right? You have north here, and then south is pointing at north, and north is like this. In this case also, if you want it to flip over, it's going to be, if this magnetic field is really, really, really strong, then getting it to flip over is going to release a lot of energy, if nothing else. So, why is this important? Well, when the right frequency of radio waves, in this case, is applied, the atoms, represented by these magnets here, which is basically what they are, can be brought into resonance. So what they basically do is they flip. And if they flip, right, and you have a really, really high magnetic field, right, you have a, large magnetic field. I mean, we're talking, I don't know, it's like thousands of Teslas, basically, right? So you have a really big magnetic field, right? They flip. They flip from favorable to unfavorable. And so then you have this change in energy. And this change in energy can be measured. Which is really good because then you have a machine that you can measure it with. And that's what we call an NMR machine. Now, how is that possible? Well, of course, if we do a little bit more theory here just for a second, we can look at this then. We can say that, okay, if we have a real atom, and of course a real atom is not like a magnet here, it doesn't actually have the spin that we're talking about here, the resonance that we're talking about here, is actually then a specific angle that is determined by, experimentally they have shown that it's a specific angle, and that the resonance then is actually then its rotation about an axis here. So if you wanted to look at it, so it creates a volume, and if what you can do is you can get this to flip over, right? And this is actually what we call then the spin. So here, this blue thing represents the magnetic field. And what you have then is you have what we call a magnetogyric ratio, which is just a fancy word. It's not a fancy word. It's a fancy word for the spin effect here. But basically, what it is it can be applied to a specific equation for this delta E. And the delta E then is equal to this gyric ratio times Boltzmann's times the magnetic field times Planck's constant divided by 2 pi. And this is the magnetic field. And this is Planck's constant, which gives us the energy value. And this converts then into this energy of the spin, which just gives us a change in energy. The reason I bring this up is that because this value here is unique. And it's unique for every type of nucleus, but also the local environment the nucleus is in. And this is really important, because if we look at a molecule, for example, we'll do exactly the same one as we did earlier, or similar to the one we did earlier, right, where we have a bunch of H's attached to carbons, and each one of these H's is of course then capable of being, is NMR, is capable of NMR, right? Nuclear magnetic resonance. Then we can see right away then that if we look at the local environments for each one of these hydrogens here are in one environment. They're on a primary carbon. These hydrogens are on another environment. This hydrogen is in a unique environment, but these hydrogens on this molecule, on this part of the molecule, are not unique, but they're unique. I mean, they're unique from the other three, but they're not unique from each other because they're both attached to a tertiary carbon with one hydrogen attached. So you have 4 local environments. And if you would look at an NMR scan for this then, you would get basically 4 different peaks. The 4 different peaks will look a little bit different though, because they're going to be broken up, or they're going to be split a little bit. So they're going to be split up, and this is the interesting thing about them. And I'm not drawing it to scale. I'm not even trying to draw it to scale, but all right, and then you'd have over here, and there'd be like there's a bunch over there. So you'd have 4 different environments, and each one represents then a different part of this molecule. So if we label this molecule these different environments A, B, C, and D, then you're going to get A, where you're going to get the highest peak for the largest number of hydrogens. So this will be something like, there'll be like a 6 up here, and then there'll be like a 1 here, and then there'll be like a little stair. Now, this doesn't always do this, but this is some sort of like pseudo-integrative process that the modern machines can do. And so this is going to be D over here, and or this is going to be, sorry, this is going to be D, this is going to be 3, and this is going to be C, because there's 2 there. So it's going to be a staircase of 1, 2, 3, 6, and then these different environments. The splits that you see here, or the different peaks, are due to hydrogen, what we call adjacent hydrogens. So let's look at this one. The adjacent hydrogen for this, here we have 6 hydrogens, and these carbons that the carbons that these hydrogens are attached to 1 carbon, and there's 1 adjacent hydrogen here. And that 1 adjacent hydrogen then causes this split, because there's like a resonance effect that causes the interference in the measurement. And it's a physical property here. And if we look at this hydrogen, this 1 hydrogen, then it's got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens on adjacent carbons. So there's going to be like 8. There's going to be actually 9 peaks or whatever, 10 peaks and 8 splits here. A bunch of them. So basically 8 splits. And the corresponding is going on in the other ones. So this is how you would, this is one way of looking at it then. And this is one way of looking at it, molecules with something called NMR. And in this case we've used HNMR, or proton nuclear magnetic resonance. And I'm going to end my movie there.